Okay, so our last talk of the day for this session is Asterisk APIs. So we're going to talk a little bit about some of the things that Asterisk gives you internally to help you do your job as a developer a little bit faster and hopefully a little bit less error prone. So when we're talking about Asterisk APIs, we're not necessarily talking about AGI or AMI or things that are available externally to people writing scripts or interfacing with Asterisk. What we're really talking about are general utilities, functions, objects, and ways of doing things inside Asterisk as a developer when you're writing your own module, your own application, your own resource, or fixing bugs or working in Chansip or something like that. And all of these that we're going to talk about are general concepts, but are Asterisk-specific implementations. So why do we have these things? For a variety of reasons. Some of these things provide functionality that's not available in C. So we have containers, lists, and hash tables and things like that, things that you would actually possibly find in C++ or other languages. We've written our own generic implementation of these to be used across Asterisk so that you don't have to roll your own linked list if you need to use one. We have various utilities to provide commonality across Asterisk so that people are doing things the same way, so that if you need to make a modification in a portion of the code base, you don't have to learn a completely new coding style or somebody else's implementation of a hash table. We have various utilities to avoid common errors, things that the C libraries do that are perfectly fine, but that sometimes people forget to check, and sometimes it opens them up to various bugs. We have various utilities to help you add additional debugging throughout your code. And the general reason is to develop faster and safer so that you don't have to reinvent the wheel. You can use what other people have already used in order to just do what you want to do when you're writing your application. So I'll talk about a few different things. String manipulations, and when I say strings in this particular context, I actually mean character pointers, so C strings. String objects, we have a couple different types in Asterisk that are a higher level way of looking at strings. Reference counted objects, containers, and some of the internal APIs in Asterisk for publishing and subscribing to internal events, and channel bridging. And we'll see how much time we have. If we run out of time, we'll pick and choose. We'll cherry pick from that list. So string manipulations. We got a family of functions for C strings. A couple of them. This is certainly not all of them, but these are some of the ones that you'll see very often throughout the code base. AST copy string, which your normal string copy that strn copy does not necessarily copy the null character if you hit the length of the buffer. So AST copy string guarantees that you'll always have a null character at the end of your string to prevent you from having non-null terminated strings and doing all sorts of bad things. We've got AST string duplication, which duplicates a string, but also will handle a null string if you pass into it. That's undefined behavior, so that prevents that crash. Various other functions for testing things in strings, stripping quotes, stripping white space, stripping blanks out of things, testing to see if something is true or false. And when I say true or false, it actually checks if it's one in an actual string value of 1, if it's the word true, if it's true capitalized, it checks for a whole various things. So that's useful if you're reading out config files and you allow somebody to say, turn on this equals true, right? So you can just pass that string and it'll tell you, yes, that's true, as all the various ways that we accept whatever true happens to be. Various ways of pulling time values out of strings, various ways of doing hash codes on strings. So everybody paid attention on this slide? Everybody remembers that? Okay, what's wrong with this code? So I've got a function. It takes in a constant character pointer foo. I duplicate foo, and then I check to see if it's null, and if it's null, I put out a notice so a guy walks into a null bar. So where's the error on that one? Anybody? Thank you. We have a winner. I have nothing to give you, but except so right. If foo is null and this gets passed into this function and I duplicate it, that's undefined behavior. Most likely you'll get a core dump and crash and Asterisk goes belly up and your calls are dead and nobody can make phone calls and millions of dollars are lost. So if we just change that with AST string dup foo, we're fine, right? Because it'll handle the null foo, it'll assign null to bar, and hey, I'm checking to see if null is bar, and I'll print out a log notice that, hey, you walked into a null bar. Okay, so C strings are great. We use them all over the place. Everybody loves const character pointers and manipulating things by accessing the pointer and everything else. But sometimes you end up writing a lot of boilerplate code, particularly if you don't know how long the string is going to be. That happens. Sometimes things come off of packets. Sometimes things come out of config files. You don't know exactly how long that string is going to be. You can constantly realloc. You can assume, hopefully, that it never hits a certain maximum length. Or you can use some of the other things that we provide. So we've got dynamic strings. They automatically grow. You can get the length of them. You can truncate them. You can append to them. You can copy them. They also support variable number of arguments in the same way that a sprintf will do, so that you can just use sprintf type characters and pass in little parts. So you can build strings directly inside this dynamic string. And if you go over your buffer length, it'll automatically increase the buffer length and prevent you from doing terrible, horrible things. We also have another thing called string fields, and these are really used for when you have a whole lot of const character pointers or static character arrays defined inside of a struct. A lot of times your configuration information that you read out of a config file is a whole lot of strings, and you need to store that information in something. So you might have a struct and you have a whole bunch of pre-allocated fields or const character pointers. This is a much cleaner way of doing that automatically will initialize all the strings for you to a particular size. It'll grow them if it needs to be grown, and will automatically deallocate. Well, it does not. It's one call to deallocate them, as opposed to having to go in and individually free each individual string when you free the memory associated with your struct. So here's an example of that. This is actually out of the code base. This is this is handling an HTTP error message, and this is using a dynamic string to do that. I trimmed out some of it, and it's still a little hard to see. But actually what it's doing right here, you can see it's calling AST_str set on the dynamic string, and then it's using printf style characters to put in strings and numbers and all sorts of things. And this information is coming out of some sort of HTTP request, and it's sending back information about why it was an error. So we don't know how big those strings are necessarily going to be, but now we don't care. The dynamic strings are going to handle that for you, grow the string if the field's big enough, and you don't have to be responsible for looking at each individual one, figuring out how big that string is, adding up, reallocating your string, and doing all the things to necessarily handle that. That's all handled for you by the dynamic string. What's the what for? Where you initially start setting the string. I'm pretty sure of that. Okay, so another one, string fields. So here's an example, and this is not this is an example of why string fields are helpful. Say I've got a widget, and my widget has a name, and I assume all my widget names are not going to be any longer than 32 characters until a customer wants widget AX123173820 serial 123, et cetera, in which case then I've got a problem. But I also have a property on my widget, property A, and I have no idea how big that property is going to be. So when I go, I write some little constructor method someplace, and I go to allocate my widget, I've got to guess how big property A has to be, right? Maybe I know, maybe I don't know, right? But I've got to allocate that property A to being something. Same thing when I go to destruct it, I've got to go and remember to actually destruct the property, and Valgrind will help you find when you forget to do that, but sometimes people forget to do that. Or I can use string fields. And I just say, I've got a string field that's a widget name. I've got a string field that's property A. When I go to allocate the object, I call string field init, and I specify an initial default size for my string fields. In this case, 128. And then I can just do AST string field set and set any one of those to being whatever value I want it to be. If it's longer than 128, it'll grow the string field, et cetera, et cetera. From the perspective of actually using string fields, it's a const character pointer const. So it's as read-only as it gets, and the only way to modify it is to call AST string field set and reset the string. When you go to deallocate the object, rather than having to remember to free every single const character pointer in your struct, you just say AST string field free memory, and it goes ahead and gets rid of them all for you. So a lot less code, a lot less things you have to remember. Makes your life a lot easier. Okay, so moving on. Next one we're going to look at is some reference counted objects. Reference counted objects are objects that automatically keep a track of how many people have said that they own that object. When that ownership hits 0, the object is automatically destroyed. So very similar to various other concepts in other languages. This is one implementation of it. But it's very useful for objects that have complex lifetimes. For example, channels, right? You might have multiple threads accessing a channel, and when do you get rid of that channel? When you know to destruct that channel, right? So the way it works currently in Asterisk, each person notifies, I'm done with this channel. And they don't have to free the channel. When everybody is done with that channel, that reference count goes to 0, the destructor for the channel, and the actual channel gets torn down at that point. There's other things that it's useful for is information that may go stale after some period of time. Rather than necessarily, you may not know when it goes stale, but you can say, well, I think this information is no longer valid. I'm going to decrement the reference count, and when everybody has decremented, it goes away. You can update your object. Things to watch out for. The reference counting is atomic, right? So that is whatever count the object has, it is that count. But that doesn't mean that if you have a global object, that's thread safe. So if you have multiple threads changing the reference count at the same time, you may end up into some fun situations where your object's being destructed at the same time somebody else still has the object. So you still have to protect your objects with thread synchronization and all the other things that you would normally have to do. And although you'd have to probably work pretty hard to do it, you can create circular dependencies on this one. If you have 2 ref counted objects and A depends on B's lifetime and B depends on A's lifetime, then they're never going away and you have a memory leak. So here's an example of turning an object into a ref counted object. I've got a struct foo. It's got a bar. And I've got a function here to make the foo and destroy the foo. So pretty standard kind of stuff. Now, pretend we've got in the code someplace where I make a foo, and then I go out and I use the foo. And I don't know what use the foo is necessarily going to do, except that it needed a foo object in order to do that. Well, at the end of that, I made the foo, so I'm going to go ahead and destroy the foo too. Well, that's great unless use the foo caches it and expects later on that that foo still exists, right? Now, maybe it doesn't always cache it. Maybe it does it sometimes. That could be optional. But in that case, you could end up in some very tricky situations in trying to figure out when you dispose of it and when you don't. Alternatively, you make it a ref counted object. So all we do instead of calling AST_calloc there, we have AO2_alloc. And we pass in as a parameter to that function the method that is going to tear down the object. In this case, destroy foo. When you do an AO2_alloc, the ref count is automatically set to 1 so that it doesn't automatically destroy itself. So when I get it, so when I say make foo, I do an AO2_alloc, I get back an object, my foo, and it's got a ref count of 1. And then I pass it off to use the foo, and use the foo does whatever it wants with it. And when use the foo comes back, I decrement the counter on it because I'm done with it. If it's done with it too, the destruction method will get called, and there goes the object. If it's not done with it, then hopefully it increased the reference count, because it really should have if it wasn't done with it, and that object persists until whatever is responsible at that point for owning it also decrements the count. Okay, moving on. Containers. So really in Asterisk right now, we provide 2 different ways of storing objects. We've got vanilla and chocolate. You get your unsorted lists or your hash tables. We've talked about other flavors, but we haven't really provided a standard way for doing that yet. So no B trees, nothing real fancy yet. All of them support thread safe and non-thread safe access. So that's real handy. If you have a list, you can just lock the list. And at that point in time, you own the list, and everybody else who wants to access the list has to also wait until you're done doing whatever you're doing on the list. Same thing with the hash tables. And all support similar operations in some form or fashion, inserting, deleting, iterating across them, things like that. Brief sort of theory stuff, the way we've had it, the way we've implemented it. If you want to add things to the list, they're a linked list. We keep track of the header and the tail, so you can add to the header and the tail in constant time. If you want to add something in the middle of the list, it's not sorted, so you're going to iterate probably across the entire list in order to figure out where you want to put your item. And you're going to iterate across the entire list if you're looking for one particular thing. With hash tables, it should be the cost of your hash function in order to add something into the hash table, unless you've got lots of collisions, in which case then we have a list that you're going to have to iterate across for all of the collisions. So, when to use lists? When you've got a small number of things. If you've got 1,000 things, lists may not be the best thing for you. If you need, however, to do the same thing to all things all the time, and you have 1,000 things, then you might as well use a list. You're going to be iterating across it the entire time, right? So granted, you'll probably tank performance in the rest of Asterisk, but, you know, hey, at least your choice of container made sense. When to use hash tables? When you care about speed, right? So, you know, in general, getting an item out of a hash table should be pretty fast unless your hash function is really, really bad. But do be careful of your hash function. You know, this is a topic that is way more complex for the talk today, and if you go look at hash functions, you'll see lots of different implementations of them. I am not necessarily going to stand up here and defend our implementation of a hash function, and if you feel like contributing a better hash function for some of the things we have, then feel free. That would be great. But at the same time, we have an okay one. It seems to work pretty well right now. In general, with hash tables, the way ours are implemented, the objects that go into the hash tables have to be ref counted objects. So when you get an object out of a hash table, it automatically increases the ref count for it. When you're done with it, decrement the ref count and, you know, move on with your way. When you empty out the hash table, it decrements the ref count on all the objects in it and assumes that they're all destroyed if nobody else is using it, which it better be. So some very common operations on the list. Lists use a lot of macros. So do the hash tables. They just aren't all capitalized. So declaring a list, you declare I've got a static list called widgets, and it's going to store a widget in it. To insert an item into my list of widgets, I call AST list insert tail. Alternatively, I could insert it on the head. That's perfectly fine. Drops a widget on the tail of the list. To iterate across it, there's a macro called AST list traverse, and I have a pointer to a widget that is the current pointer, and it'll just go through every item in the list, kind of in a for loop, and just pound through them, iterating across them. Hash tables are a little bit more, take a little bit more in order to do things. You have to write 2 callback functions in order to use a hash table. You have to write a callback function that provides the hash, right? So we have to know how we're going to take your custom struct and stick it into the hash table. So you have to tell us how you want to compute a hash key for your object. We've got a couple different methods that do that. That if you have a string, we have AST str case hash, so you don't have to roll your own. You can use what's provided in the string libraries to do it if you've got strings. Alternatively, if you have unique IDs or some other ways of doing it, you can roll your own hash function. And then you also have to have a way to compare 2 items if you have a collision. So remember that if you have collisions, we put it on a list, and so then it starts looking for all the items on the list to see which one you're actually looking for. So you have to provide those 2 functions. You have to write those 2 functions if you're going to use the hash table. The hash table, by the way, is an AO2 container. In this case, I've got one called widgets again. Now, actually using it, though, isn't so bad. To allocate it, I just call AO2 container and alloc. I define the number of buckets I want, in this case 283, because that's a prime number. And I provide my hash function callback, and I provide my comparison function callback. And that gives me a container called widgets, which is a ref counted object again. So if I want to just completely get rid of it, I just decrement the ref count on it, and there goes all my container and all my objects. To insert into it, I can just do an AO2 link call that automatically locks the container. If I don't want it to lock the container, there's a flag I can pass in and say, no, don't lock the container. But in general, it'll automatically lock it for you to prevent thread safe access to the container. Same thing with delete. When we call unlink, we actually don't delete the object. We just drop the ref count by 1. So you can unlink an object out of the container, but as long as if somebody else is still using it, you don't affect them. Eventually you will when they signal that they're done with the object, but you don't automatically remove the object for them. Searching it's a little bit more tricky, but not too bad. You have to create an object, a temp object that you're searching for. So in this case, I've created a temporary widget, and I said it is widget X, because that's the key field for it, right? So I want to look to see if I can't find widget X in my container. So I call AO2 find. AO2 find takes that temp widget with a field of widget X and looks to see in widgets if there's a matching widget with the name widget X. If there is, gives it back to me. If not, I get a null. So if I do get it back, the ref count has been gone up by 1. So I am responsible for, once again, decrementing the ref count once I'm done with it so that I don't have memory leaks. OK, so the next 2, and actually we're doing OK on time, so that's pretty good. The next 2 topics I'll kind of look at from a very high-level perspective. These are APIs inside Asterisk that can help you do various things depending upon what your application wants to do. One of them is the Asterisk Event Framework. It is a general publish-subscribe framework within Asterisk where you can subscribe for events and publish events to various things within Asterisk. So you could have a channel, for example, that publishes a security event. And other channels or other things could be monitoring for those security events and respond appropriately if that security event goes out across the system. So it's a generic pub-sub architecture. Right now we've got a few different things in there. This is actually how voicemail message waiting indicators work. So when app voicemail essentially recognizes that a new voicemail has been left, it kicks off an event that says, I've got a new voicemail and the count is this. And all the channels and everybody else who's interested in a new message being left have subscribed to that and say, oh, I've got a message. Do whatever is appropriate for my channel technology to notify people that there's a message waiting. There's device state changes, security events. This is also how the channel event logs work. So there's lots of room for expansion in this. This is a generic architecture that we've put these types of things in, but they may be useful for your application. You may actually want to also expand on them if you have a complex scenario where you need to signal between multiple threads that various things have occurred. This is thread safe in the sense that somebody who's publishing an event, it actually goes out on a separate thread, so it doesn't clog up their thread. And the people who have subscribed to it aren't serviced on that same thread. It's serviced on a completely separate thread. Another API that has been added fairly recently is our channel bridging API, which is an API for connecting two or more channels in a very standard way. If you look at some of the code in, for example, app dial, a lot of this stuff was done manually, or in features.c, a lot of this stuff was done in, we're going to bridge these kind of channels, and it's one large method or a couple methods that do this. This is an actual standard API for exposing that functionality to any application that needs to do that. So you've got, and it'll automatically do various things for you. It'll automatically support various technologies. It'll automatically handle video. It'll automatically do codec negotiation between the channels that you're bridging. It's got various features that it supports in the API, doing blind transfers, three-way transfers, doing an actual dial to a new channel. And this is actually the technology that ConfBridge was built off of in Asterisk 10. So that's a good starting point if you're interested in doing some sort of bridging, or if you want to write a custom application for doing bridging, that's a good starting point to see how to use that API. Questions?